So we're moving on to questions here about amino acids and peptide or amide links. And this first question is asking you to draw the structure of the zwitterion formed by phenylalanine. Now bear in mind you don't need to learn the structure of phenylalanine. It is provided in the data booklet. And it looks like this. Now from there, what we've got to consider is A, what we mean by the term zwitterion, and B, how we can form it. And the whole key principle around zwitterions is that they have got both a positive and a negative charge. Now if I take a look at the example that we have here, I've got NH2, which I am aware of in the context of being a base, and I've also got COOH, which is a carboxylic acid group, so acting as an acid. So I've got something that can act as a proton acceptor, and I've got something that can act as a proton donor. And the reality is, with amino acids, that we will end up with this structure as the zwitterion of phenylalanine. So the COOH has lost its H+, the NH2 has gained an H+, and we end up with our NH3+ and COO- components of the overall structure. Now we then have got to consider the structure of serine at a high pH. So again, we go to the data booklet, we find serine within that data booklet, so we know what it looks like. And what we've then got to consider is that serine has a high pH. If it's a high pH, that means that it's alkaline. And that means it's going to act as an acid, it's going to act as a proton donor. So it will donate the NH2, it will donate the H from the NH3+, leaving NH2. It will donate the H+ from the COOH to leave COO-, and we end up with this structure that we can see here. Draw the structures of both dipeptides formed when phenylalanine reacts with serine. In each structure, show all the atoms and bonds in the amide link. So the first thing that I've done here, before I even consider the question, is I've drawn out phenylalanine and serine so that we can very clearly see what we're working with. We also need to remember that the peptide link is a CONH. So we know that we're losing an H from the NH2, and we know that we're losing an OH from the COOH. That's water, gone, it's condensation, and we can then consider how that peptide link forms. Now there are two forms here, depending on which side the phenylalanine and the serine fall on. So in the first example here, you can see that I've done the phenylalanine on the left, and therefore providing the C double bond O, and I've got the serine on the right, and that's providing the NH of the peptide link. And you can see I've drawn the peptide link out in full. I've shown the display formula, all atoms and bonds. Now what we then need to consider is what if the serine was on the left and phenylalanine was on the right? Well, this is what we end up with then. And you can see from the colour coding which parts have been lost in each example as we have put them together. And then we move back into mechanisms. So on this one, we've got an acyl chloride, we've got a primary amine. We need to know what the mechanism is, we need to know what we're making, and we need to know the name of the mechanism. Now, I'm actually going to leave the name of the mechanism till last, because as I say, whenever I go through one of these questions, I think it's really important that you understand why the mechanism is called what it is, why it is that type of mechanism, more than simply trying to remember it. That depth of understanding is going to be of huge help when you're trying to learn so many of them. So let's start off with the mechanism itself. I've drawn out my two reagents, and I've put the lone pair on the N on the NH2 because that's a really important part. You might now be thinking about what that amine is going to be acting as, because that's going to go into the name of the mechanism later on. But we can also be thinking about where it's going to attack. And we've got our first two marked right here. It's going to attack that carbon, and we need to understand why. Well, that carbon is bonded to a delta negative oxygen and a delta negative chlorine. So that's two very delta negative atoms withdrawing electron density from the carbon, making it very delta positive and therefore very susceptible to attack from the amine. Now from there, the second mark, we move on to the double bond being broken. Well, logically, the double bond is going to break because we've got 5 bonds around the carbon at this stage. So that removes electrons, it removes a bond, and we end up with our carbon back to having 4 bonds around it. From there, we get a mark for the intermediate structure. And you can see that we've got the N is now positive, and that's really important. We can see the O has a lone pair of electrons, and the O is negatively charged. So we've got to mark number 3 for this structure. From there, we're going to reform the double bond. So we're back to 5 bonds around that carbon, which isn't sustainable. Something else has to change. So we lose the Cl at this point. The Cl has gone. The O has reformed its double bond. The carbon is back to having 4 bonds around it. And finally, separate to those 2 arrows, we are going to get rid of the N+, and we do that by losing an H and those electrons moving in to the N. So we're going to get a lone pair back on that N. Now, the 4th mark in this mechanism is for having all 3 of those arrows in the correct place. What type of mechanism is it? Well, to begin with, it's nucleophilic. I'm hoping that when you look at the N with the lone pair of electrons, that's telling you nucleophilic attack. So we're part way there. Now, you might be tempted to go for substitution, but actually substitution would have been the chlorine being lost straight away, and that isn't how this happens. So we're not substituting, we are adding something, and then we're eliminating something else in a different step. And so for this one, it's nucleophilic addition, elimination. And finally, we have the name of the organic product. So it is an amide. We can see that we have got propanamide, which would be the CONH2. But one of the H's on the NH2 is substituted by an ethyl group. So it's ethyl propanamide, but the final bit of notation here, we put the N in front of the ethyl to show that the ethyl is coming off the nitrogen within the amide.